Well, good afternoon, everyone. Welcome to day 2 of Smart Buildings Week. I'm really glad that everybody could join us today. This is a week of webinars that's produced by the Smart Building Center, and we're just missing a couple of things on my screen. We're very pleased to have a great group of sponsors that have made this whole week possible. I want to give them some quick acknowledgement, from our title sponsor, Microsoft, to the McKinstry Company, Seattle City Light, Puget Sound Energy, DB Engineering, Long Building Technologies, McDonald Miller, ATS Automation, the Seattle King County chapter of BOMA, the Washington State Department of Commerce, and Belimo. So thank you to each one of those sponsors. My name is Stan Price, and I'm joined today not only by the panel that you see on your screen, but a colleague of mine at the Smart Building Center, Britton Reif, who you do not see, but whose magic fingers will be controlling a lot of our Zoom call today. So you may hear her name mentioned from time to time as we move throughout. I do want to mention at the outset a couple of housekeeping notes. First off, we are recording this event. And so if you want to go back to it later or refer others to the information today, we'll be posting that on the Smart Building Center's YouTube channel in the next week or so. I also, most of you are probably very familiar with Zoom by now and know that your camera and microphones have been disabled. But that doesn't mean that we're not wanting to hear from you. There's a question and answer box that's available to all of you. If you have questions throughout the presentation today, please do put them in the Q&A box, and we'll monitor that on an ongoing basis throughout today's discussion. So we're going to jump right into things. I'm really pleased that we have two moderators today for our panel. Ben Levy from Seattle City Light. Ben, give us a wave. And Mark Linson from Puget Sound Energy. So those two will be guiding us through a conversation with a panel that they're going to introduce to you right now. Ben, start us off.
Thanks a lot, Stan. I have the honor to introduce two of our panelists who are thought leaders in the industry of energy efficiency and as well as electrification. So we have Mark Frankel, who is currently Director of Technology and Innovation at a local engineering firm, Ecotope. And he was formerly from NBI. And then we also have Mary Ann Piet, who is from the Lawrence Berkeley Lab, and she is the Director of Technology and Director of Building Technology and Urban Systems at the lab. So, Mark, who else do we have? Yes.
All right, thank you. Thanks, Ben. I have the pleasure of introducing quickly couple of the other panelists today. Kara Carmichael is from the Rocky Mountain Institute. Thanks, Kara. And Alexi Miller from the New Buildings Institute. Thanks, Alexi.
And could each of you give us a 30-second quick bio on your interest in this area?
This is Mark. I will start. I've been working on grid integration for a couple of years, starting at NBI until last year when I moved over to Ecotope. And at Ecotope, we focus more on the design side and how we integrate build grid integrated features into the building sector. I'm very excited about this space. I think this is a huge area of growth, and we'll have a great discussion today.
Hi, yeah, Mary Ann Piet here, Lawrence Berkeley National Lab. We're doing research here on energy efficiency, but also demand response and demand flexibility. And so we're very interested in supporting a change in the electric grid and supporting the reliability, affordability of the grid. And we care not just about how much energy we use, but when we use it. So we're doing a lot of research to support automation like OpenADR working with both DOE, California, the Northwest, and others around the country.
Hi, folks. I'm Kara Carmichael. I'm a principal at Rocky Mountain Institute, and my interest in grid interactive buildings really stems from the fact that buildings are the largest emitter of carbon emissions globally, and so that makes them in a prime position to be a key part of the solution. And so by enabling grid interactive buildings, they can really serve as the linchpin to system-wide decarbonization because they provide such great and crucial benefits on the grid side. So we've been doing a lot of thinking around the value of grid interactive buildings to building owners, and as well as the carbon value of demand flexibility. And I guess just a short point is now is a really key time in the industry. So I'm excited to be here today. Thanks for pulling it together and look forward to chatting.
Hi, I'm Alexi Miller with New Buildings Institute, and I lead the Grid Optimal Buildings Initiative, which we're now in our third year actually, working on that initiative. And the purpose of the Grid Optimal Buildings Initiative is really to build a bridge, if you will, between both sides of the meter or across the meter, so that we can have new metrics and new ways so that the needs on the grid side, including emissions, can be translated to folks on the building side, whether that's designers or owners or others, in ways that they understand and can do something with. So dealing a lot with metrics on that, and also some sort of design guidance kind of stuff. And I'm motivated by some of those same issues that Kara mentioned, that basically, if we're going to achieve these deep system-wide grid decarbonization and societal decarbonization goals, then we need buildings to actively help support that and not stand in the way. So I think building grid integration and grid integrated efficient buildings, the stuff we're going to be talking about today, this is kind of future-proofing buildings and making sure that buildings form part of the solution, not part of the problem.
Okay, terrific. Thanks, everyone. So to start things off, we're going to ask Mark Frankel to do a short overview of grid interactive energy efficient buildings and kind of provide us with the basic definitions and the concepts that we're going to need to understand this issue.
Great,
Mark?
thanks, Ben. I will say this is an unenviable task to introduce a topic that's going to take us years to resolve in 5 minutes. And I will also tell you, attendees, that the panel group here has been talking about this for years. And so if we get carried away in acronyms and topics that you don't understand, please ask for clarification. So I'll pick up my pace so I can get through this really quickly. So you all know that we have set grid carbon-free goals for the grid in the US. Some regions are tackling this aggressively. The West Coast and East Coast have really aggressive goals to decarbonize the grid. There's a lot of renewable energy sources coming onto the grid, and these are less controllable. They're more episodic, and we can't dispatch them in the same way as we can conventional resources. But even though we have all these new renewable resources, we still need peak load at peak times, and whether that's coincident with the renewable resource or not. So you've all heard of the duck curve. Next slide, please. This is the way it's playing out in California as they add solar to the grid. In the middle of the day when the sun's out, there's more and more sun available, so a greater and greater percentage of their daily load is generated by solar. But in the evening and in the morning before the sun comes up, they still have the same peak load as they ever had. So the head of the duck, if you will, on the right side, you can imagine their peak load is just as big as it ever was, and it's after the sun goes down. So they still have to have all the same grid resources, the peak power resources on the grid available to the grid to meet that load, even though they never get to use those during the day because the sun's out. So those resources are more and more expensive to run relative to the annual use of those. And so the utilities are driven to start thinking about how can we change the shape of our load to match the shape of our resource. Next slide, please. So what you see in the on the grid nationally is that the amount of time we use our existing resources goes down more and more and more. So in the 60s, the grid resources, that is the generating plants, were used over 65% of the time. And now, you know, in the in the teens, we're down below half the time. So coal plants and gas plants or whatever use less than half the time. So you can imagine how the utility has to pay off those plants even though they don't ever get to use them. Next slide, please. So the legacy grid, of course, the conventional power plants were able to distribute load to buildings and whatever loads in a fairly predictable way, and it was always one direction. It was always the utility supplying the power that they anticipated was needed on the grid. Next slide. The new grid is actually much more complicated, more like a game of Tetris, because there's buildings and cars and all kinds of things putting energy into the grid and taking energy out of the grid at all times. And it's very, very complicated. The amount of data needed just to control this is massive, and few utilities are really capable of controlling this in the same way. So now we need much more interactive control, and we need these individual loads to respond, to be able to respond, control, and influence the way they interact with the grid. So what does that mean at the building level? Next slide, please. We can think about the load shape of the building. If you have a base load, and very oversimplified, say an office building where people arrive in the morning and the load increases to the day, and we get to the point where we have a peak, and then as people go home, it drops off. So the original way to think about load shedding was automated demand response, and that's the little bar or little box at the top there where the utility says, we have a crisis, we need to reduce our load, can you help us? And some percentage of the building stock says, sure, we can cut our load by 15%. They turn off a chiller for an hour or what have you, and that's the automated demand response there at the top. But now we're talking about more complicated things like shifting the time at the building peak. So if you have a lot of sun coming in the morning and you want to shift to use more energy then, maybe with a battery system or whatever, we're changing the shape of the building load to match the availability of resources. I want to point out that there's also a role for energy efficiency still, because we're reducing the total load on the grid, which is good, and we conceivably are reducing the peak load on the grid, peak reduction. So all these are different ways to manipulate the grid, the way buildings use energy and interact with the grid. Next slide, please. Those shifts are referred to in different terms, which you'll hear. Shift, which we change the peak. Storage, where we might capture energy and use it later. Shape, shed, which is reducing total energy use, and shimmy, which is changing the nature in a very short term to manage load energy quality. So Z&E has played a role in this shift very significantly. Z&E buildings were maybe some of the first to start pouring energy back into the grid in a somewhat uncontrolled way, as individual buildings build PV arrays and expect the grid to take that solar. So it's important to think about the role of Z&E in grid integration. On the left, and this is courtesy of a study by NREL and RMI, on the left is a building load shape where the orange is the typical load shape that peaks in the afternoon with cooling. This is probably a load shape. And the green in that upper left graph shows the amount of solar needed to net that out over the course of a year. So in the middle of the day when you have a lot of sun, you're making more energy than you're using, and then over the course of the year you take it back in the evenings and it all nets out to zero. On the bottom you can see that we're expecting the grid to supply power when that line is above zero, and then take all our excess PV when we have more to generate, and then give it back to us at night. So you can see the swing through the grid in the lower left graph. We're actually relying on the grid to be our battery, and it's a big impact. On the other hand, if we start manipulating the way the building uses energy on the upper right quadrant, we shift some of the load, we add efficiency, and we basically lower the total load of that building. Then we need less PV to meet the load, so that's cheaper. But also, if you look on the lower right, our impact on the grid is much lower. So that's a really important demonstration of how building performance and load shape can change the impact on the grid, even in a net zero building. Next slide, please. So because of the availability of information in real time, Internet of Things, if you will, there's a whole bunch of new industries that are becoming engaged in building energy use. And it's pretty surprising. This is actually an ad from Mercedes-Benz, where the car is going to start controlling the house and get signals and what have you. And it's pretty amazing the technology and the capabilities that we're starting to integrate into smart appliances and personal technology and renewable systems in cars. All of these are becoming part of the interactive grid. So there's a lot to work with and a lot of technology and information out there. This kind of load flexibility from a study by the Brattle Group will represent a 15% reduction in peak demand by 2030. And I guarantee you that as more renewables come onto the grid, utilities are going to be more and more incentivized to send a price signal to make sure that buildings are responding to their ability to provide peak power. Next slide. So finally, I want to point out that this is definitely changing the building industry. We're going to have to respond in real time to changing utility price structures. Designers are going to need to understand and incorporate these strategies that allow buildings to interact with the grid, and this is going to play out for building owners and commissioning agents very much so as well. And this is going to be critical to building services comfort and resilience. Thank you.
Great, thanks, Mark. I'm going to kick off the first official question to Kara. So Kara, can you start this conversation by helping us understand the key differences between the classic demand response programs and today's topic of grid interactive efficient buildings?
Yeah, thanks, Mark. Good question. So I think that there are a couple of key differentiators from how we approach our buildings today. This is kind of true in general as well as how it applies to demand response programs. So first is the interoperability and intelligence between buildings and the grid. The second is this level of interoperability and intelligence across building level systems. So how we heat and cool and light and fuel our cell phones in our homes and office buildings. And then the third is really this concept of load flexibility and demand-focused optimization, not just energy-focused optimization. So really with demand response programs today, they're often manual. I've heard them referred to as sneaker DR. So literally somebody in their sneakers runs around the buildings, you know, flipping switches and turning things off. And it's a fairly static interaction. It's kind of surgical demand response events, just responding to a couple-hour period of time, one-way signals. Oftentimes demand response is met with fossil fuel resources, which is helping but hurting in another way, helping the grid but hurting in another way. So I think in the future, we'd really like the ability to send and receive and respond to utility price signals in real time. And also one interesting ability would be for buildings to actually send any potential load flex opportunities they have back to the grid, so it could be more of a dialogue. I'm going to focus on kind of that first row. DR today also targets mostly large commercial and industrial customers, and the penetration across the US was less than 10%. So I think that there are opportunities to not only make DR programs more impactful, but also significantly expand their participation. If we go to the next slide, please. And as Mark Frankel began to touch on, like buildings drive 80% of grid peak demand. So DR is a really important solution in the market today, and will become even more so as we have higher penetrations of variable renewable generation on the grid. These peak times are also really expensive. More than 10% of grid infrastructure costs are spent to manage less than 1% of their time to meet the need during those spikes. So it's super expensive and likely carbon intensive times of day. Next slide. So just to touch on if, you know, demand response, when we're optimizing for carbon versus cost, those end up looking like pretty different solutions in buildings. You can see demand response programs are often targeted in the summer and shoulder seasons, in the afternoon hours, kind of where that blue box fits. But if we're looking at the carbon intensity on the grid, that's pretty variable across seasons, and especially within different days on the grid. So if we're optimizing for carbon, we're going to see a lot more seasonal shifting, which is something we're trying to get better at from a systems-wide perspective. But we're also going to see a lot of, you know, shifting within hours of the day. And that's a real opportunity that we can harness today in today's, like with the technology that we have in today's buildings. So I guess I would part on the demand response piece with, I think there are a couple big opportunities in demand response programs today. Integrating energy efficiency and demand response programs, today they're fairly isolated, but merging those two, thinking more on a real-time basis is a big opportunity. I think also this conversation about empowering aggregators, ESCOs, curtailment service providers to actually provide solutions in a way that often utilities aren't nimble enough to do, but I think if we can empower them to create more of these solutions, it's really going to be a big part of the market.
Do any other panelists, oh, thank you, Tara, but do any other panelists have any thoughts on that too? Or have you seen examples of where utility programs or aggregators have merged energy efficiency and DR?
Yeah, there's been some projects in California where the utilities were looking at controls retrofits. And retro commissioning is a great example of where you go in, you get the controls working. And really, if you want to do automated demand response in a large building, you really should do that commissioning first and make sure your temperature set points and your sequence of operations and your supplier reset, those things are there first. So you don't try to start manipulating a sequence in the controls on a building that's got some fundamental controls problems. That's one of the foundational things for large buildings. And in homes, similarly, if you put a smart thermostat in a home that has a lot of leaking problems, a lot of windows and no insulation, it's not going to perform as well as a building where you've gone in and do those energy efficiency improvements.
Great, thank you, Marianne.
Okay, so for the next question, Marianne, back to you. If grid interactive efficient buildings are about a dynamic two-way communication between buildings and the utility, help us understand what data are being shared and an idea of the technology needed to make that happen.
Okay, so my first slide, I'm going to take off a little bit where Mark started, and he mentioned the shape, shift, shed, and shimmy, and I'm going to talk a little about what those things mean and how we automate them. Shape is responding to tariffs, and time of use tariffs are coming to many parts of the country in the Northwest and California. So we want to shape that electric load, and that may be something we do every day or seasonally where the prices change. The most important thing I want you to remember is that we're working on ways to get the prices to the devices. So that I'm going to show you in a moment a picture of the California's price server framework that we're working on. But when we think about automation, we need to send some sort of signal. Things like OpenADR and CTA 2045 have been tools to get these automation to devices. And then the device has to respond. And the device may respond by responding to a time of use price, or it may respond to a more dramatic shift call, like we thought about when we see the duck curve. We want to use more electricity when it's clean and less electricity during the dirtier parts of the day around dinner time when there's less renewable energy. So we shift load by getting maybe even a carbon signal or a price signal. And in the future, you might be able to have a controller that says, I want to be super economical right now, or I want to be really clean. I'm willing to pay a little more to be clean, or maybe those are together. So we want to look at things like watt time or OpenADR and be able to receive signals that require these end node technologies to respond. Shedding still has value. So here in California, we had blackouts, and there were a lot of aggregators that were calling their shed programs. So I want to make sure that we understand that the complexity of the grid, and shedding is something we use for reliability and contingency, or when there's super high prices. So we have these different things we want the building load to do. And then shimmy is the fast acting services, might be voltage or regulation services. And those are often automated with 4-second telemetry systems. So we may have help to stabilize the local grid with voltage regulation, sending a load to a variable frequency drive or a battery. And these things are acting very quickly to maintain the voltage on the grid and provide services that we really are trying to get demand side systems. If we can get a lot of this from demand side systems, it is lower cost than going straight to batteries. So we want the buildings to be part of our ecosystem. And I also want to mention something called set and forget. So you can say, I want to do this at 20 cents and I'm willing to do a little bit more at 30 cents. And if we could set those prices into our automation, our devices will respond if they have a 24-hour ahead price signal of some sort. Go ahead to the next slide. So this is an example of what the California Energy Commission is proposing for a price communication system. We are moving towards digital tariffs. So it's a very exciting time. We've been trying to do prices to devices for quite some time, and we now have a lot of technology that's going to allow us to do that. So the utilities would be required to offer a signal associated with time of use, critical peak pricing, real-time pricing, or even transactive pricing. And these signals would be communicated. You can see 5-minute prices on there and even FM broadcasts. So on the right, you see the different types of devices that will be enabled to listen to and respond to those devices. And we want to provide an ecosystem. One of the things that Kara mentioned was the need to do energy efficiency first. So that is, we don't want to have inefficient loads responding. We still want to invest in energy efficiency first and lower the load and then make the load dynamic. So again, we're looking at not just how much energy you use in your home or your building, but when you use it, and trying to get your consumption patterns aligned with grid signals to allow us to have a more affordable, a more reliable, and a cleaner grid. And I'll stop right there.
Okay, thank you, Marion. And just a side note, or maybe something the panel can respond to, I read this morning that the California ISO said, oh, you know, the reason that we're having brownouts is because you guys aren't allowing us to have enough generation capacity. So what we're posing here is a solution which would be not entertaining that and going the other way and just having lots of demand flexibility. Do you guys think that that is the solution to California's problems going forward, or do they still need to have dispatchable energy in California?
I'll take a first pass at that, if I may. It reminds me of how we got efficiency in the Northwest and California, for that matter. Remember the WHOOPS program, where we were going to build all these expensive nuclear plants, and then we discovered that we were putting enough debt on each individual residential meter in the order of $40,000 per house or whatever, and that whole thing collapsed. And the feds bailed us out by requiring us to look at the least cost plan for new electricity supplies in the Northwest. And so that's why we have this proud history of efficiency, because that turns out to be cheaper than building nuclear plants and a lot of other plants. Well, now it's going to be even more that way when we think about meeting certain times of day loads. You know, it's really expensive to run peak gas plants or whatever compared to solar, which is the cheapest new energy out there. It's cheaper to build new solar than to run existing coal plants now. So that equation about least cost resource is going to very much come into play with time of use.
And just building on that a little bit, there are several different ways that this problem might be solved. It's going to be more than one at a time, of course, but you could put in a whole bunch of batteries or you can use your buildings as batteries. And so some of the strategies we're talking about here could obviate the need for both large scale and small scale storage to some extent by enhancing this flexibility. So you can, these kinds of strategies may get us to a place where we've achieved basically the same results of keep the lights on when they need to be on at a reasonable cost without unreasonable environmental impact through some, you know, hopefully optimized combination of generation and storage and demand flexibility or time of use energy efficiency strategies.
Hey Ben, this is Carrie. We've had a couple questions come in from the audience, and there's one here that I think is somewhat relevant to the discussion that Mark and Alexi were just having. The question, folks, is DR possible without price signals? And then there's some specific questions around when we might see some time of use rates implemented in the Pacific Northwest, which you may or may not have the answers to.
We could ask our utility guys when the time of use rates are coming, but they're coming. I think they are coming, no question.
Yes, we have somewhat of a, we have nighttime rates now, I guess, for large customers, and we obviously have demand charges, which are sort of akin to some of this. I mean, if you want to reduce your overall bills, then you definitely don't want peak charges. So that's sort of a stepping stone to get to the next level. But as you guys know, I mean, utilities are kind of slow and they like to follow some other utility. So we'll probably be following in California's footsteps, I imagine.
Can I make a comment about demand response without price signals? There are certainly reliability programs where the wholesale market calls DR when, that's actually what happened in California a few weeks ago, was we were approaching our capacity limit and they called the DR, and the programs that aggregators offer are not tariff-based price signals. They are market-based price signals. So they pay a capacity payment for the demand response to be available when it's called, and they'll sign up for 2 hours or 4 hours, and they'll sign up to give so much load. Maybe it's homes and they'll give a kilowatt, or maybe it's large buildings and they'll give 50, and they'll get paid for what they deliver during those events with a baseline. And that's one of the differences between the price signal DR versus the capacity market ones, where you have to calculate a baseline, and the baselines are always a challenge because of weather normalization and industrial loads that change over time. But when it's built into a tariff, there's no baseline, it's built into the bill. So you don't have to settle outside of the bill. So that's one kind of basic, that is traditional demand response. It tends to be hot summer days or cold winter mornings during extreme sort of grid events.
And there's also another model that Watt Time is working to enable, which is where there's a real-time carbon signal that goes to the device level. So their vision is that you might have a dishwasher, say, and you say, okay, full, there's soap in it, run it sometime in the next 12 hours when it's clean. And that's not really about the price, that's about the marginal carbon on the grid. So that's relies on some intelligence. They have that real-time 5-minute marginal carbon signal up and running. So it's hopefully not too far away.
I'll add one thing to that, if I may. We worked on a project in California that was trying to use a carbon signal to minimize their carbon footprint. And we actually had to convert it into a price signal to feed it into the battery controller, because the battery couldn't understand it if it wasn't a price signal. So.
All right, well, I'm going to keep us moving forward. So, Alexia, I was wondering if you could tell us a little bit more about how both building and utility load shapes might change with the robust GEB grid-enabled buildings capabilities if they're widespread in new and existing buildings.
Sure, yeah. So I'll mention just at first, as I mentioned, we've been working on the Grid Optimal Buildings Initiative. One of the things we started with is what's out there right now, to say what's the baseline we're working from so that we can see how might these load shapes change, like you're saying. So there's the website to Grid Optimal. There's some resources there, more coming shortly. But if you go to the next slide, I call this kind of the Grid Menagerie. Mark mentioned the duck curve, and of course there's our beloved duck. It's not all ducks everywhere. There are an increasing number of places that are coming up ducks, and that includes Hawaii. The nene is pretty ducky. It's a native Hawaiian goose. Up in the Northeast, there's enough solar coming on in some places like Vermont that they're getting a little bit ducky. But there are also other grid shapes or other conditions that are happening on the grid scale. For example, in Texas or the Midwest, there's a lot of wind on the grid. So in Texas, say, the armadillo curve refers to a situation where you have a lot of solar during the day and the wind peaks at night, and there's this little spike of unserved load in the middle. It's supposed to look like the ear of an armadillo, maybe after it got squashed flat, I'm not sure. But there's that spike in the evening where you're not getting solar and you're not getting wind. So just as Mark was saying earlier, you still need all these resources available, but you kind of got a double whammy where many of the hours of the day and the night, you don't necessarily need them, but you need all of them briefly. So what we're seeing, as Mark said, is we get more variable resources integrated into the grid on a bulk scale from buildings and from big installations. We're getting either things like ducks, where we've got low net load during the day, or things like armadillos or alligators, where we've got wind impacting. And Texas is the time scales, maybe daily. The Midwest gator, the idea there is that the wind can be pretty spiky and variable. So, and for that matter, so can solar, if, clouds are blowing across. So there are these larger time scales, hours, and much larger, obviously seasonal, like in the Northwest, where there's a ton of hydro in the spring and very little in the fall. But there's also the very short time scales that we need to figure out what to do with, whether that's getting a whole lot more juice from a lot of places on the grid, or whether that's other strategies, like when the wind is bouncing up and down quite a bit. So there's a bit of the grid side that we're dealing with. There's different load shapes in different regions, as mentioned. And then on the building side, I'm going to get to that in a minute. And maybe actually, I think these are slightly disordered for the way I think it might make sense to do this. Can you go to the next one? Yeah, okay, perfect. This is what I was hoping to see. Great. So Pierre Delaforge from Natural Resources Defense Council has this article, or this idea. He likes to think of heat pump water heaters, for example, as clean energy batteries. So this is a graph from Pierre. And this is an example of what you might be able to do with a device. This could be in a home, or you can use heat pump water heaters certainly in commercial buildings too, to be able to shift the load around and adjust the load shape that this device is contributing to. In a single family or multifamily home, a whole lot of the load is actually water heating. So this could be a pretty significant aspect there. So what this is doing, and I should caveat that the way we have manufactured, installed, and operated heat pump water heaters today doesn't necessarily do this. This is kind of what might we get out of a technology if we did all kinds of neat stuff and really, used it to its full potential. You could, for example, take a signal, say, oh, today would be a good day to preheat my water, use up some extra power during the day when we might have a lot of abundant, clean, and affordable electricity. And then you can coast through those afternoon and evening hours when there might be higher water demands, when folks come home for the day, without needing to really run that heat pump water heater very much, if at all. And then you can do some recharging overnight. So that can actually, if we were able to pull that off on a large scale, the preheating is a little challenging with the way we run these things right now. But if we were able to, really leverage this capability in heat pump water heaters or in other devices, then we could have buildings that not only shed load, but also can take load and bank it up for later. And you can store a lot of energy in water or in the space of a building. One thing that I'm trying to do through Grid Optimal is find ways to communicate actionable recommendations or how do we get there from here, so that a building designer or someone else in this space can do something with this. Because the duck curve and this heat pump water heater, here's what we might get to. These are fascinating, but they're a bit abstract, and you kind of got to get the intro and wrap your head around it for a while. So what we've been trying to do to build the bridge between what the grid needs and what the building can do is put together some metrics. And I think the next slide shows several building grid integration metrics. These are the ones we've published through Grid Optimal. They're not the only metrics, and we'll cover a couple more in a minute. But these are some of the categories that I think it might be useful to give a brief overview of to get an idea of kind of what buildings might be able to do and how we can measure it, because having the ability to measure it means we can put it in programs, we can give incentives for these kind of performance outcomes, and it can go into other things. One example actually of other things is LEED. We anticipate pretty soon here having a grid harmonization pilot credit that uses these metrics that you're seeing. So I'm not going to go through all of them, but grid peak contribution, that first one, is a lot like what we're talking about today. That is, how closely does the building's load shape line up with the grid's load shape over the whole year or at specific times of the year? You know, how similar are these two curves? On-site renewable utilization efficiency has to do with maximizing self-consumption of on-site renewables, which can have value to the grid, especially in a distribution sense. And then the third one I want to cover specifically is this grid carbon alignment. Just like grid peak contribution is about matching up the grid system curve, megawatts, with the building demand curve, kilowatts, grid carbon alignment is similar, but it's about how closely does the building's demand line up with the carbon emissions associated, or greenhouse gas emissions associated with electricity on the grid scale. Are you using a lot of energy when it's dirty, or are you using more of your total energy when it's relatively clean? And then there are a couple others around flexibility and resiliency as well. These are largely, the way we've built these metrics is largely about comparing a building to the building's maximum for the year, right? The building's peak demand over the year, how close to your peak are you? That gives you some kind of a unitless percent. And all these are actually quantified metrics. I've got a white paper out and they're on the website. Happy to noodle more on that. But these give you some kind of a percentage rating. It's also useful to think about things in watts per square foot. So if you go to the next slide, these are some metrics that Marianne and her team are working on to talk about shed and shift. And maybe I'll just pass over to Marianne to give a quick overview of these metrics as well.
Thanks, Alexi. So I know there's a lot of complexity here, but the main thing I want you to take away is that watts per square foot in the upper right-hand corner. So I've got blue is taking energy and orange is shedding it. So these are events that are for 4 hours where you have a commercial building and you've done something. You may reset the temperature. And when you reset the temperature, it gets warmer. So the bottom is the what we call operative temperature, which includes some radiation and thermal comfort metrics. So it's not just the air temperature, because the temperature around you influences your comfort. So we want to make sure we understand when we reset the temperature 3 degrees, 4 degrees, how quickly does the building warm up? And that is dependent on the mass. But we also look at shades and lights and maybe pre-cooling. So the building, when it acts as its own sort of thermal storage, some buildings do better. If you have a lot of surface area to volume, it's going to be harder to do. Or if you have a lot of windows, it's going to be a little harder. But a library is a great one with all those books and less windows. So the watts per square foot is this number here where we get maybe half a watt a square foot. So we divide by the square foot so we can compare buildings of different sizes. We could compare a 100,000 square foot building with a 200,000 square foot building. And we show in green the net kilowatt hour change. If we pre-cool, we don't want to waste that energy. So we want to take some energy and we want to shed some energy and move it from times of the day without using too much more energy over the day. Because if we use a lot more energy, it could cost a lot more. So depending on how the prices work in those different times, we're calculating the watts per square foot to increase and to decrease, and then the net change over the day, and also looking at how temperatures change inside the building. So that's the basic idea here, is to have some things we can compare across buildings in models as well as in real buildings. So we're collecting data from real shed events and shift events and trying to understand how models and real buildings compare as well.
Okay, terrific. Just to keep things moving, I wanted to ask Mark if he could kick off a discussion about how how we do this practically. So how can both the building owners and the utility derive value from having the grid enabled capability? And we can kind of go around the horn or keep this a lively discussion at this point.
Sure. Well, I'll toss out 4 quick things that we can talk about. One is, I personally think time of use pricing is inevitable. I mean, our utilities are going to be in a world of hurt with what we're requiring of them if we don't give them a way to sort of incentivize a different load pattern in our building stock. So I think it's inevitable. We are seeing it in California. New York's had it for decades. It just doesn't happen to be about renewables. It happens to be about midday peaking in the city. And even in the Northwest, Snohomish PUD has adopted a time of use pricing pilot program that they're trying to get people to respond to. So it's coming. There's also the carbon goals, as Alexi mentioned. You know, I've certainly worked with projects, we probably all have, that are setting carbon goals, and they want to know when should they use energy to reduce carbon the most. And so, you know, there's a lot of big industry that's made carbon commitments and individual projects, and we're going to see more and more of that becoming a motivator. And, you know, in the Northwest, we have a law that our utilities have to be carbon free by 2045. And so that's going to drive it as well. PV integration, you hear a lot of people around the country whining that the utility won't pay for their PV at the rate they charge them for power. And you know, it's not just that utilities resist PV because they don't control it. It's that, you know, in California, they pay other states $50 a megawatt to get rid of their PV in the middle of the day. So they're paying other states to take power that they have to buy from customers. That is not a sustainable economic model. And so the idea, you know, if you're thinking about net zero buildings, the idea that you're just going to dump all this PV on the grid and make them be your battery, I think that's going to have a limited run. And then finally, resiliency is really critical. And a client we had in California, we talked about batteries with their PV array. They were doing all this stuff I mentioned for carbon. And they got their permit last year, right about the time that the big power shutoffs happened for fire. And all of a sudden, they didn't have any power in their building. They called us up and said, you know what, we want the batteries after all, that they had decided that were too expensive in the first place. So the kind of flexibility and grid interaction drives resiliency in many different scales. So there's a lot there we can tease out, and others can jump in.
I would add, I think that resilience point is really important, like especially as we're facing outages across the US and different grid territories for very different reasons. Storms, weather, you know, the smoke events and utility, you know, shutoffs. So I feel like there's a growing movement for people to have more control over their energy supply. And I think there's a lot of ways you can do it through traditional diesel generation, but you can also do it with solar storage efficiency in a way that's going to provide much more significant benefits to you as kind of a consumer in the long run. I would also add that RMI has been doing quite a bit of analysis both on federal portfolios as well as large portfolios across the country. And what we're finding is that even as a precursor, as you know, time of use rates get rolled out, there's still a tremendous benefit in having demand flexibility in your buildings. And we estimated that it could save up to 20% of utility costs in GSA's portfolio. And that spans across different utility rate structures, utility zones, climates. It's kind of normalized for that. So I think there's cost benefits today, even with today's rate structures, and it's just going to future-proof your building against future rate structure changes, resilience, pieces like that.
Could I jump in, Ben and Mark, and ask the panel a more specific question in this regard? I'm interested, sort of springing off of your last comment, Kara, about the value proposition to building owners and managers, that there may be some cost savings opportunities sort of embedded in this approach. And I'm wondering whether or not that's sort of the sole and exclusive value proposition for folks on the building side, or whether or not there are value statements here associated with things, the other things that building owners and managers care about, which is, tenant satisfaction and wellness and productivity issues within the buildings, better and enhanced control in general over the indoor environment in their buildings. Are there things here that can sing that song to make market adoption of these sorts of strategies go more quickly for folks on the building owners and manager side?
So I have
I'm sorry, that was a long question, but there was a question mark at the end of that.
So I have two comments. One is your favorite retail store, Target, has 1,000 stores across the United States doing demand response. They're probably the most successful retail chain, and they're committed to do it. Most of it's automated with OpenADR. They get signals from aggregators, and they put a sign up, that we're in an energy conservation event. So they're trying to understand the value in very different markets across the U.S. with very different timescales. Some in 5-minute markets, very fast ER short events, 20-minute events, some multi-hour events. And they helped here in California over the last few weeks. So they are understanding, are their controls ready for this emerging marketplace? And how do they have different vintage stores, some have electric heat pumps, some have electric resistance. So different kinds of HVAC systems. Clearly they're all retail stores, and they do lighting. So it's not just HVAC. So I wanted to make that comment as an example of a kind of an owner that has made a major investment. The second one I want to mention is the power saving shutoffs, the public safety power shutoffs that we have in California. Here at the lab where I work, we've been looking at bringing in temporary diesel generators for those few days a year where we're preparing. But what I want you to know is putting the building into some kind of low power mode. So when we go on our backup system with a battery, we don't run the building the same way we would in our full service mode. So the idea of the future building codes may have an emergency mode or a low power mode where the building can maintain some level of service in a resilient mode. That's at a, the lights are 50%, the HVAC deadband is extended, turn off half the plug loads, some sort of strategy to green the building. And that's a very valuable concept it's extending these demand response into more extreme low power operations.
I guess I'd add one other thing at the risk of opening a new topic, but we're selling tens of thousands of electric vehicles to customers, and they know they have a big old battery that they would like to maybe integrate with their house and think about, instead of paying demand charge, I'm going to just take off the top of my battery. So we think batteries are expensive, but we're deploying them as transportation, and there's every reason to think we can integrate those in the building sector as well. Sorry, Kara, go ahead.
No, it's a great point and kind of feeds on what I was just going to add, is that we can't ultimately have this level of grid integration and interactivity if we don't have the fundamental controls in our buildings to ramp up and ramp down when needed, and to actually integrate all of our today fairly siloed end uses under one platform. And I would say that platform will reduce the complexity. I mean, what we're talking about here is not simple solutions, for that, they require some thought and some planning and some level of automation. And so we need a major investment in our buildings to upgrade the control system so that they can adapt, respond to the signals in the right way, and actually communicate with one another so that we can operate kind of more nimbly. So I think that's one of the barriers kind of holding up grid interactive buildings from scaling. We can do it. I think it's becoming, the control systems are capable today. We just need to see more of it.
I'd say there's a related barrier just to pile on. All these electric vehicles, for example, or stationary storage in a building, if you're a utility and you're hooking up a new line to a building that's got a battery in it, there are certainly plenty of folks in the distribution planning departments of utilities who see that as one more big old load. And so that means you need more service. So it costs more to provide electricity to the building that has the battery that, by what we're saying, should be used to help solve that problem. And so if we have the right kind of controls and the utility can be truly confident that, okay, this battery is not going to be charged when every other load is on, then we can find a different value stream entirely to the building in reducing the size of their service, reducing their hookup fees, if and only if the utility can really know that they're not going to have this big problem that they might otherwise need to solve for. And that's an issue with electric vehicles. That's an issue with any of these strategies, really. If it happens, if you do it backwards, it makes the problem significantly worse. So part of the solution needs to be, kind of like Marianne said earlier, commission the buildings, make sure they're not out of whack when you start. And there's a second kind of commissioning too, to make sure that the solution itself is always, or at least statistically always, if you know what I mean, going to be helping to solve and not hurt.
Thanks, Alexi. I'm going to hit up the last question here, and then I'm going to target this at Marianne. I wanted you to maybe talk a little bit about the current situation or recent situations in California, and with the utility system having some serious issues in recent weeks. So I was curious if you could talk a little bit about if there was a robust GEB fleet of GEBs, grid-enabled and efficient buildings. Would that have helped in this scenario? What are your thoughts on that?
Yeah, I think all of the electric utilities and the aggregators are very proud of the demand response that did come online during the call. Let me just give one example that I'm very aware of. Ohm Connect actually received a call from the state asking them to try to get as much as they could out of their customers. And their model is interesting because they have thousands of homes, mostly homeowners, and they 50% of the shed that they get is automated. They sell devices, and then the other is manual. So they actually ask people to do things. And they called customers 8 days in a row. They had 4-hour events, and normally they'll call for 1 or 2, but they actually called for more hours, and they actually called customers without getting paid on the market. So they were trying to sort of do what they could from that resource and pay their customers, but really creating quite a value to the state. And they have very good data on what they actually were successfully able to do. So the utilities are very aware of the crisis that we were seeing. And I know the state, the university, the UC system, the University of California, were also asked to curtail. They were actually asked to go on backup generation, which normally we do not do in DR because of air quality. So a lot was happening behind the scenes, and a lot of buildings we had a couple of days of blackouts, but we were able to get through several days without them, and because of demand response and grid interactive efficient buildings.
You know, actually in this last heat wave before the big fires, so mid-August, Tesla actually sent out a little ping to its owners in California and said, hey, this is a good time to avoid supercharging or charging 4 to 9 p.m. I don't know I don't know if anyone here knows numerically what happened as a result of that, but they were able to say, now's not a great time to charge your car because we're experiencing demand issues as a state. So there's a modern example coming in.
Or actually, that's a traditional example of demand response, right? And what we're trying to get to is this more automated thing. And I think of the way Seattle City Light and probably PSC thinks about it is like, we have actual we don't care as much about generation. Somebody brought up on the questions about hydropower and how all that figures in. Hydropower, we have plenty of it, and we're just looking for more load almost. But when we think about costs and savings, we're thinking more on the distribution end. And if we can reduce our distribution costs because buildings in a particular area of the city are using less for those peak times, we don't have to pay for more substations, we don't have to pay for reconducting lines. So that's the part that the utility really seems to care about. And that's a good stepping stone, I think, to get to getting these things into buildings, because if the utility can deal and negotiate with building owners better, we might have a way to go forward a little bit without just going all the way to the time of day, time of use pricing.
Well, sadly, folks, I'm going to jump into this conversation because it's 1 o'clock and formally thank all of our panelists and our moderators for a really engaging discussion today. And I invite our audience to come back again tomorrow for Chapter 3 of Smart Buildings Week. I'm going to ask Britton to stop the recording now.